SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss about heat transfer from the extended surfaces. Heat transfer rate from a surface by convection process is proportional to surface area, the heat transfer coefficient, and the temperature difference between the surface and the fluid. Temperature difference and the heat transfer coefficient for a given situation are fixed. Surface area is to be increased artificially so as to increase the heat transfer. So there is an effort to increase the surface area so that the heat transfer is enhanced because of enhanced area. So, as we have already said, that heat transfer coefficient and the temperature difference for a given situation are fixed. So these extended surfaces are called fins or spines, and their purpose is to increase the heat removal between the surface and the surrounding ambient fluid. And surrounding ambient fluid may be flowing fluid, may be a static fluid. Some of these fins can be seen on air-cooled engines attached to car radiators, condensers, refrigerators, boiler tubes, or many other heat exchanger devices. Now here we have typically given example of some fins. First one is called rectangular fin. It is basically, some rectangular section or rectangular projection will come out from the base. Second one is called trapezoidal fin. Third one is called triangular fin. Basically these names are coined based on the shapes. And the fourth one is concave fin. Typically one fin I have shown from some industrial usage. You can see how the fins are sometimes fixed on outer surface to enhance the heat transfer from the flowing fluid which will be flowing inside the tube. It will heat up the tube and then the tube will be again transferring heat to the fins, and entire set of fins together with the tube will be cooled by the outside ambient fluid. Now for an analysis we have taken a protrusion from a base in the form of a cylinder, or you can say in the form of a body which is having arbitrary shape. It may be triangular fin, it may be rectangular fin. So we'll see, we are trying to first derive the general equations. So here you can see this is the base which is having a temperature T0, and this is the extended surface. And on the extended part at any distance x, if we take a cross section, the heat transfer rate is given by QA, and delta x apart we take another cross section, heat transfer rate is QA plus del X into QA into delta X, since it is delta X apart. Now, if this is the energy coming through this section and this is the energy leaving through this section, and there is a difference, that difference is basically taken away by the surrounding fluid in the form of convection, and that is given by H, the convective heat transfer coefficient, ds, area of interest, and T minus T infinity. If its local temperature is T, ambient temperature is T infinity. Now, and at the end, we are saying whatever is the area, end area, again there will be heat transfer, but we have written HE deliberately. Normally HE and H are same, but for a special situation it can be different. For example, for high speed flows which are flowing cross flow over, for example, this object, now there the effective H on this surface and effective H on this surface may be different, but in case of quiescent fluid, it is expected to be same. So what we will consider is steady state heat transfer. Conductivity K of the fin is constant. Heat transfer with the solid in the heat transfer within the solid in X direction only. There is a small printing mistake. This will be within the solid in the X direction only. This is possibly only if the area of cross section is small compared to the fin length and the boundary conditions are constant with respect to Z and Y direction. Z and Y direction, basically the boundary conditions are same. That means boundary conditions are same around the periphery. This is not rectangular geometry, so appreciating that is difficult. So, as I said, around the periphery, at a given X, along the periphery, basically boundary conditions are constant. Another implication of the third assumption is that the temperature will be uniform across a cross section of the fin. So that means the cross sectional area is given by AX. It may be a function of X, cross section may vary. Sx is the surface area of the fin from X equal to 0 to any given X. K is the conductivity of the material and H is the heat transfer coefficient of the fin surface. Now, heat transfer by conduction to the left face of the element QA, we have already said this, and heat transfer, this is by conduction, and heat transfer by conduction out of this area, this given control volume or area of volume of interest is QA plus del QA del X into dx. Heat transfer by convection from the surface ds of the element exposed to the fluid at a temperature T infinity. So local fluid temperature is T infinity. That means H into ds, the surface area through which convective heat transfer will take place, into T minus T infinity. And what we have written here is T average. So we are considering average temperature over this volume of interest. T average is the temperature of the element or average temperature of that elemental volume. Now from first law of thermodynamics, we can say QA equal to QA plus del x of QA delta x plus H delta S into T average minus T infinity. And we can easily recalculate this as del x of QA plus H into ds by dx T average minus T infinity equal to 0. In the limit of delta x tends to 0, delta x is basically this distance. In the limit of delta x tends to 0, del s by delta x is ds by dx. So delta s by delta x, under the limiting condition, it is ds dx. That means differentiation of the surface area, and average temperature tends to T, local T. So we can write from this equation A dq dx plus q dA dx plus H ds dx multiplied by T minus T infinity equal to 0. If we substitute Q equal to minus K dt dx, the heat flux, as such, if we look into this entire calculation, we have always done heat flux into area. Q is the heat flux. Although earlier we have defined Q double prime, here we have written Q, it can be redefined. So heat flux into A, that is the total energy coming in, and that QA we have, QA plus del x of QA into dx going out, and that is how we have constructed this problem. So here Q is basically the heat flux, and it is given as minus K dt dx. So if we substitute Q as minus K dt dx here, Q as minus K dt dx here, so here we'll get minus K d2t dx2, and here we'll get minus K dt dx. And then you can see, and then we divide the entire equation by Ka, and then we'll get d2t dx2 plus dA by dx divided by A dt dx minus H by Ka ds dx into T minus T infinity equal to 0. To find a unique solution of this equation, we can see second order differential equation. Two boundary conditions are needed since the order of the equation is 2. So at x equal to 0, the fin will have the temperature of the base. We have written metal, it is material rather, base material, unless there is some contact resistance problem. So this fin, the way it is attached, if there is, attachment is not continuous or not smooth, if it doesn't form homogeneous isotropic extension, then obviously there will be some contact resistance. But we are ignoring that situation here. So at x equal to 0, t equal to t naught, at x equal to L, He, the end surface heat transfer coefficient, Ae, the end surface area, A T minus T infinity temperature difference equal to minus K conductivity into Ae area of interest, area of end surface into dt dx. That means whatever thermal energy is conducted till the end, that is being convected. This is the end condition basically here. So at x equal to 0, t equal to t naught, and at x equal to L, we get this condition, which is basically convective condition. So first we'll analyze fins that have same cross section all along its length, and such fins are amenable to simple mathematical analysis. And we can see this can be rectangular or circular, so that we always get constant cross section along the length. So this is the breadth, this is the length, T0 is the temperature at the base, T infinity is the temperature of the ambient fluid, H is the heat transfer coefficient. And here heat transfer coefficient is He. As I said, H and He are same, normally, but in some conditions, some situations, they can be different. Have a generalized paradigm, we have considered He as different, but if it is equal, you will see there is no problem. And this is a fin which is having a cylindrical shape. And R is the radius, D is the diameter, and L is the length. So here B is the width, T is the thickness, cross-sectional area is BT, and perimeter is 2 into B plus T. And the total surface area up to a given x is perimeter into x, and from here we get ds dx equal to always the perimeter, and dA, since it is constant, dA dx is 0. Similarly, if r is the radius, area is pi r square, and that area will not change, so dA dx is 0, and perimeter is twice pi r, and surface area is p into x, so that ds dx equal to p, and this p also doesn't change. So this gives some sort of easy situation for solving this problem. That means this part, this term will be dropped. If this term is not dropped, then nature of the equation will be slightly different. We'll solve such situations later, but today we will consider the cases where this dA by dx divided by a dt dx, this term can be dropped. So we will drop that term, and the governing equation will be d2t dx2 minus, we can easily see from here, right, my ds dx is p, so it will be minus hp divided by ka, hp divided by ka, t minus t infinity equal to 0. Substituting theta equal to t minus t infinity, and m is a quaint parameter, right? M means h into p, heat transfer coefficient into perimeter, divided by thermal conductivity into area. M is a parameter of which is basically comes out of combining these terms, but it has no typical I would say physical meaning, but can be interpreted as the ratio of a form of convective resistance and conductive resistance, or conductive resistance and convective resistance, because 1 by h we have to now bring in the denominator, and then readjust the terms in such a way that conductive, this heat transfer coefficient by conductivity can be expressed that way. We'll come to that point little later, but d2 theta dx2 we get from here minus m squared theta equal to 0. Now d2 theta dx2 minus m squared theta equal to 0, this equation can have three solutions, three possible solutions, all are same. One is theta equal to c1 e to the power mx plus d1 e to the power mx. Another is c2 cos hyperbolic mx plus d2 sine hyperbolic mx. And another is theta equal to c3 cos hyperbolic m l minus x plus c3 cos hyperbolic m l minus x plus d3 sine hyperbolic m l minus x. So any solution we pick up, we'll see after proper substitution of the boundary condition, solution we will get is the same. Now x equal to 0, t equal to t naught base temperature, we can say x equal to 0, theta equal to theta naught. Theta is the excess temperature over the ambient temperature. So it is T naught minus T infinity, which is theta naught. At x equal to L, minus k dt dx equal to He T minus T infinity. So minus k dt dx into end area equal to He into end area T minus T infinity. End areas are same, it get cancelled out, and so we can write minus k d theta dx equal to He into theta. Now I have written case 1. This is slightly unfamiliar because in such configuration, I have not mentioned, I will mention it later again, that these fins can be considered, such fins which are having uniform cross-sectional area throughout. One is called basically end heat transfer coefficient is defined, and it is convective heat transfer. Another is infinite long fin, and another is the end condition is adiabatic. That means at the end the heat transfer is insignificant. So these three cases, case 1 where there is finite heat transfer in the form of convective heat transfer at the end. Now substituting these boundary conditions, so theta equal to C3 cos, we have taken the last one, C3 cos m L minus x plus D3 sine, C3 cos hyperbolic cos h m L minus x plus D3 sine hyperbolic m L minus x. So basically solution is in the form of e to the power minus x and e to the power plus x. So we have to take either cos hyperbolic function or sine hyperbolic function to match this requirement. So C3 cos hyperbolic m L minus x plus D3 sine hyperbolic m L minus x is the solution we take. And for x equal to 0, t equal to t naught, if we substitute x equal to 0, theta equal to theta naught, so it will be theta naught equal to C3 cos hyperbolic ml plus D3 sine hyperbolic ml. So first condition has been substituted and we get this expression. Second condition is minus k d theta dx equal to He theta. So minus k, and we differentiate this quantity, we can get minus mc3 sine hyperbolic L minus x minus md3 cos hyperbolic ml minus x. So this is equal to He into theta. Again we write the expression for theta. This is k d theta dx equal to HE, this is theta. At x equal to L, if we substitute x equal to L, we'll get K, this will be dropped, we'll get Km d3 equal to He. In He expression also, we will get basically this will be dropped. So we will get from here d3 equal to C3 He divided by Km, and now we define He by Km as uppercase H. This is again a definition. He is end heat transfer coefficient by thermal conductivity into M parameter, and this is M is quite often called Finn parameter. So C3 into H. This is substituted as H. Now from here we can write C3 cos hyperbolic ml plus H sin hyperbolic ml equal to theta naught. That means C3 basically D3 we get in terms of C3, and this D3 we substitute as C3 into H, and then we take C3 outside the bracket and we get this expression. From where we get clear expression for C3, theta naught divided by cos hyperbolic ml plus H sin hyperbolic ml, and D3 is nothing, whatever is C3 into H. So theta equal to C3 cos hyperbolic ml minus x plus D3, this is D3, sin hyperbolic ml minus x. That is the complete solution. So we can write in a more arranged way, theta by theta naught equal to cos hyperbolic ml minus x plus H sin hyperbolic ml minus x divided by cos hyperbolic ml plus H sin hyperbolic ml. And also we can write what is the value of H. So theta by theta naught is cos hyperbolic ml minus x plus H sin hyperbolic ml minus x divided by cos hyperbolic ml plus H sin hyperbolic ml, where this uppercase H means He divided by Km. Now the heat transfer through the fin is basically, fin is cooling. So mechanism I can just once again highlight. So surface will be cooled by the local fluid, local ambience, and that will promote heat transfer, that will bring down the temperature, and from the base energy will flow through the fin. So the base will be cooled, base temperature will come down if continuous energy transfer takes place, because energy is continuously taken away by the ambient fluid. So here we can write Q fin is Q at base minus Ka dt dx at x equal to 0, or minus K, the cross-sectional area intersection between fin and the base, that area into d theta dx x equal to 0. So Q fin, then we can differentiate this d theta dx, and this is minus Ka minus m is common from both the terms taken out. We get inside sin hyperbolic ml minus x plus H cos hyperbolic ml minus x after the differentiation. and denominator is cos hyperbolic ml plus h sin hyperbolic ml. Sorry, again a printing mistake. This is not lowercase l. This should be uppercase L. At x equal to 0, theta 0. So Q fin, then we can write basically Ka, and m is root over hp by Ka into theta multiplied by this term sin hyperbolic ml at x equal to 0, h cos hyperbolic ml at x equal to 0 divided by cos hyperbolic ml plus h sin hyperbolic ml. So this is the consolidated expression for Q fin. Root over Ka hp. K is the thermal conductivity, A is the area, H is the heat transfer coefficient, P is the perimeter, root Ka hp into theta naught multiplied by hyperbolic function which is sin hyperbolic ml plus cos hyperbolic ml divided by cos hyperbolic ml plus sin hyperbolic ml. So this was, as I mentioned, case 1 where end heat transfer, end surface at the end of the fin heat transfer condition is convective heat transfer. There are two other cases. One can be infinite long fin, that is x tends to infinity and theta tends to 0. And another is insulated fin. That means at x equal to L, minus k d theta dx, minus sign I have not written, it is same, k d theta dx equal to 0. So, first we will, it is very easy to extend this analysis for insulated tip fin. For insulated tip fin, basically what will happen, we can see that k dt dx will be 0. That means this he by km, which is which comes from here, this should be 0. So basically this uppercase h, this parameter will be 0. And then in this expression, if that is so, we can see here uppercase h is 0 means d3 will be 0. So in the foregoing analysis, d3 equal to 0, which will give c3 equal to theta by cos hyperbolic ml, which will in turn produce theta equal to theta naught. C3 is theta naught by cos hyperbolic ml. So theta equal to theta naught into cos hyperbolic m L minus x divided by cos hyperbolic ml. So the solution, so this is typically that fin which is from end heat transfer can be neglected. So along the length, everywhere, through extended surface, there will be heat transfer, temperature will come down, but at the end d theta dx is 0. So here it is theta naught, here d theta dx is 0, theta distribution along the length is something like this. So theta equal to theta naught, and this if we expand cos hyperbolic m L minus x, will be able to write theta equal to theta naught e to the power m L minus x plus e to the power minus m L minus x divided by 2 cos hyperbolic ml. Just we are rewriting this. So theta by theta naught, we can write twice cos hyperbolic ml minus x divided by cos hyperbolic ml. Then, Q fin or the heat transfer at the base, where theta equal to theta 0 is minus k dt dx at x equal to 0, or minus k d theta dx at x equal to 0. So we find out the derivative of this term, expression for theta, and substitute x equal to 0. We can see, you can do step by step, that it will be finally root over ka hp into theta naught tan hyperbolic ml. Very easy and straightforward. From the previous solution, we get a special case where h is 0, and then we get the form of theta by theta naught. We differentiate d theta by dx, and we get the expression, substitute x equal to 0, and we get this root over ka hp theta naught tan hyperbolic ml. And that is what we have written here, that this is the first case where convective heat transfer takes place at the fin end, at the tip of the fin. There we get this solution. Insulated tip fin, we get this solution. And if we very simply try with this solution, theta equal to c1 e to the power minus mx and d1 e to the power mx, or what we used for other two solutions, and substitute this condition that x equal to infinity, theta equal to 0. Temperature will gradually, temperature difference, excess temperature over ambient temperature will be 0. A tip will be at the ambient temperature. This will be the solution, theta equal to theta naught e to the power minus mx. And heat transfer coefficient, like these two cases, we have calculated Q for convective heat cooling condition. This is the Q fin, and for adiabatic fin, this is the Q fin. And so exactly those expressions we have written here. And for infinite fin, x equal to infinity, this is the Q fin. Now x equal to infinity specifically I have not derived. I have derived in detail A and B, C, these two cases. B is very straightforward. I am leaving it on to you to derive this. Now, efficiency of a fin. There is one criteria which is called effectiveness of a fin. Effectiveness of a fin is basically minus k dt dx at base divided by h T naught minus T infinity. Heat transfer rate from the fin, heat transfer rate from the base in the absence of fin. So obviously it will be always greater than 1. The second criteria, which is used as an index of performance of the fin, is called fin efficiency. Fin efficiency is heat transfer rate from the fin surface divided by heat transfer rate, which would occur if the entire fin surface was at the base temperature T naught. So exactly what is the heat transfer rate? If we do perform the surface integral over the surface, h into t minus t infinity into ds divided by h into t naught minus t infinity into s. So difference is that here this integration has to be performed because t is basically function of x. That means with the s it changes in the x direction, but here it is constant throughout h t0 minus t infinity multiplied by s, the perimetric area. And this is the final expression we can write, and we can calculate this also. Efficiency of a straight fin, the fin which we have handled, complex fins we have not handled in this lecture, we will be doing in the subsequent lectures. So h into, this is total complete area into theta naught, and this is q naught if basically only surface area has to be considered. Remaining is theta into entire surface area. So that we have geometrically twice BL, B is the width and L is the length. So top surface and bottom surface twice BL, twice LT, L is the length and T is the thickness. So two sides and BT, that is the end or cross section, end cross section BT. So this we get. And Q, which is basically, again, integration of t minus t infinity into ds. This can be, root over k hp theta naught tan hyperbolic ml. And that is the result we got, actual Q, if we look into our analysis. So we have taken that actual Q, and then in actual Q we substitute the geometrical parameter a and p. A is twice b plus t into bt and theta naught tan hyperbolic ml. So fin efficiency, that means this Q expression, we divide by Q naught and do little bit, algebraic calculations. And this is very simple. Just you have to do some simple algebra and cancel out the common terms, and we will get the expression as this. Now this can be further reduced. Here we can write this as eta f equal to tan hyperbolic ml into all these remaining terms, which are basically tan hyperbolic ml. This will constitute ml, and by ml into 1 plus t by b, 1 plus t by b plus t by twice l. Now 1 plus t by b plus t by twice l can be approximated as 1 plus t by b. This ratio is close to 1. So fin efficiency is given by tan hyperbolic ml by ml. So here we if you have any doubt, you can just look into it carefully from the resource material, and it is very simple algebra. I have not discussed step by step. I have given what is the expression for L, and finally ML, and then how does it look like, and exactly we get this term root over 2h ml equal to L into root over 2h by kt 1 plus t by b to the power half. So this terms can be just if we bring ml in the denominator, this 2h divided by root over kt will come here, and this will go here, and we'll get basically this term. So this is what we wanted to say. These are the simple fins which are having uniform cross section. We can have three cases. End condition is defined by convective heat transfer condition. End condition temperature tends to ambient temperature, fin is so long, and in condition there is the heat transfer is so small that we can consider it as insulated tip fin. And insulated tip fin and the end condition when convective heat transfer takes place, we have analyzed that today in detail, and also we have just discussed how fin efficiency can be defined, that is heat transfer rate from the fin surface, actual heat transfer rate divided by heat transfer rate which would have occurred, again there is a mistake, which would occur, no, it is correct, heat transfer rate which would occur if the entire fin surface was at the base temperature T0. So we got that. Now, in the analysis of fin with constant cross section, you will see that we can have a few other examples also. Maybe in practice problem you will get such problem, but here we have to always remember hyperbolic functions. Sine hyperbolic x is e to the power x minus e to the power minus x by 2. Cos hyperbolic x is e to the power x plus e to the power minus x by 2. So e to the power x minus e to the power minus x by 2, and cos hyperbolic x is e to the power x plus e to the power minus x by 2. If we remember this two, we can easily find out tan hyperbolic x, cot hyperbolic x. Not only that, the differentiation of sine hyperbolic x becomes cos hyperbolic x, and differentiation of cos hyperbolic x becomes sine hyperbolic x. So these are the hyperbolic functions have to be used in all straight fins, means all fins with constant cross-sectional area. So we will stop here today. Thank you very much for your attention. We will handle fins with little more complex shapes in the next class. Thank you.